Greetings, Brian here, and we're going to do some review today for our exam on April 17th. And there's 5 topics which are going to be covered on this test. Magnetic fields and forces, that was in chapter 24. Electromagnetic induction and electromagnetic waves, that was the material of chapter 25. We had quantum mechanics, that was the material of chapter 28. And nuclear physics, that was the material of chapter 30. So it's those 4 chapters, 24, 25, 28, and 30. Those are the chapters we're going to be considering on our test. And spot the physics about how it starts. Before we start the review, I want to do kind of a quick, kind of like finale, grand finale to the story of nuclear physics. So here's an interesting thing. If you took 2 high energy particles and you slam them together, and they do this at the Large Hadron Collider, in CERN in Geneva, Switzerland. So they have these 2 particles come in and slam together. So the 2 particles are moving really, really fast toward each other. They slam together. You end up having this dramatic kind of like collision and a lot of energy in the collision. And the energy's got to go someplace. And what it can do is it can come out in the form of extra particles. And one of the things they do at this Large Hadron Collider is they take these particles, slam them together, they both stop. The kinetic energy they had has to go someplace, and it makes new matter. So suppose it had a collision that had a combined energy of 1.2 tera electron volts. Now tera is 10 to the 12th. So I have 10 to the 12th electron volts. What could I make with that? How many protons could you make? I want you to do a quick calculation of the number that you would get, and I'll be back. Well, of course, to calculate that, we would just use our most famous equation in the world, E is equal to mc squared. The energy that I get is 10 to the 12th, or 1.2 tera electron volts, 1.2 times 10 to the 12th electron volts. If I convert that to joules, I can ask myself, how much mass can I make? And the mass that I can make, or want to make, is like an individual proton. An individual proton has a mass of 1.67 times 10 to the minus 27th kilograms, and so I could solve it that way. The other thing I could do is I could note that a proton has a mass that's approximately 1 atomic mass unit, and we know 1 atomic mass unit is about 931.5 mega electron volts. So it's approximately equal to 1 giga electron volt. And this is 1.2 tera electron volts. So we have more than 1,000. If you complete the calculation, you get 1,280 protons. So you slam these 2 particles together, and what comes out, you could make this many protons. That's a lot of mass. Now, in fact, what comes out is not a whole bunch of protons, but a whole bunch of different particles. And this is a picture of the tracks that came out of such a collision. You hit these 2 particles together, and you get these tracks, and they curve different directions because there's magnetic fields, and some of them are positively charged, and some of them are negatively charged, and some of them have big masses, and some have small masses. They're at different speeds, but you can just produce a lot of stuff. You can produce a lot of stuff. And the really interesting thing you can produce, and the really interesting stuff that you can produce, is things that nobody has seen before. You can produce particles that nobody has seen. And that's why this whole device, this Large Hadron Collider, was built primarily to look for one particle called the Higgs boson. And we wanted to see if it could produce Higgs bosons. And in fact, the machine was able to produce them. Now, there was a worry that when this thing was turned on, you slam these particles together and produce exotic forms of matter that nobody had never seen before. What happens if we produced a black hole that swallowed the Earth? Could that happen? The answer is no. It's stuff that nobody has seen before. And the reason we know this is true, the highest energy cosmic rays, 3 times 10 to the 20th electron volts. There are high energy particles hitting the upper atmosphere of the Earth that have 10 to the 8th times as much energy as the pathetic little Large Hadron Collider. So it's ridiculous, 100 million times as much energy. When they hit the upper atmosphere, they make all kinds of crazy particles. This has been happening since forever. Think about this. The highest energy cosmic rays they're probably protons. So I have an individual proton that has as much kinetic energy as a baseball pitched at 60 miles per hour. When that proton hit you, it could knock you over backwards. That's kind of nuts. Actually, it would just punch a hole through you. But in principle, if it transferred its momentum to you, it could knock you over backwards. Nuts, nuts, nuts. Particle accelerators like the Large Hadron Collider have been producing new particles for a long time. And they're really fascinating. One I want to bring up that's kind of an interesting thing that's produced in vast quantities in these kinds of interactions is this thing called a neutrino. And neutrinos are these tiny little neutral particles. They seem like they've got just a very, very tiny mass. They're neutral. There's no charge. And they only interact extremely weakly with other matter. As a matter of fact, the sun produces these in vast quantities. And right now, every second, if you hold out your hand, 6 trillion neutrinos per second are passing through your hand, and with apparently no ill effect. And if the ultimate state of the universe or fate of the universe and what happens to it in the future is quite possibly dependent upon the neutrinos and the masses of the neutrinos. They're tiny, but they're incredibly important and a subject of big study in physics these days. But also, in addition to neutrinos, there are all these crazy particles that are created, this particle zoo with all kinds of different charges and masses and spins, et cetera, et cetera. And people try to get a handle on these by saying, like, we're producing hundreds of different kinds of particles. Maybe we can understand them in terms of underlying constituents, like all the elements in the periodic table can be understood in terms of protons, neutrons, and electrons. 3 particles make up the whole table. Can we do the same thing with these particles? The answer is we can, and they're made up of quarks and leptons. And a proton is made up of 3 quarks, a down quark and 2 ups, and a neutron is made up of 3 quarks, 2 downs and 1 up. And so you've got 3 families of quarks. You've got up and down and strange and charm and bottom and top, and you have their associated leptons, which are electrons and positrons, muons, et cetera, et cetera. And it seems to be this is it. These are basically the fundamental particles plus bosons. I won't talk about bosons, but you have basically these particles and these families of quarks, and everything is made up. And it was a really fascinating end to the story, but it seems like there's just these 3 families of particles. Why are there only 3? And you seem to have this like matter and antimatter. You've got electrons, you have positrons. Why is the universe made of matter as opposed to antimatter? Because antimatter seems like it works basically just like normal matter. So in the early stage of the universe, there was equal amounts of matter and antimatter. How come matter gets to call the shots and not antimatter? And there's all kinds of interesting questions you can ask about this. And you reach a point where if you ask these kinds of questions, like why is it so, the answer is at present just because. This is just how it is. We don't have theories that explain why. We just know that is the way of the world. And we're starting to basically say, what is the next realm of questions that we can ask? Why is it that way? Well, let's ask these questions and try to get some answers at them. We're at a very, very interesting point. And we've reached the point in this course when I've taught you basically everything there is to know about physics. That's chapter 30. So it's time to double back and think about chapter 17. But before we do that, it's time for a bit of review. And the first piece of reviewing is reviewing the concepts. So what I want you to do is take a look at some of the multiple choice questions in the textbook, or take a look at some of the problems that I posted on the exam review on Mastering Physics. And each one of them is designed to be kind of a straightforward one-step problem that just helps you review the basic concepts. So for instance, here's one from the textbook. Number 19 from chapter 24. It's about an electron moving near a long current carrying wire. And the question is this: what is the direction of the magnetic force on the electron? I want you to look back if you have to, but analyze this and don't just jump ahead to the solution. Work through this. Can you figure out the steps that you need to do? And you're supposed to vote on the answer. I'm not exactly sure what the voting is for. And anyway, we can't do hand signs because we're doing social distancing, so let's not worry about that. But I want you to say, what is the direction of the force on the electron? Take a moment, think about it. I'll be back. Well, the first piece of the puzzle is this. There's a current going in this direction. So since there's a current in this direction, there's a magnetic field. And if I put my thumb in the direction of the current, my fingers curl in the direction of the field is coming out up above the wire, and it's going in below the wire. Okay, so the magnetic field lines are looping around, and they're making circles that go like so. And so if I look at the electron is exposed to a magnetic field that comes out of the paper. The electron is moving to the right, so it looks like so. So the electron's moving to the right. The magnetic field is coming out of the paper. If it was a positively charged particle, that would predict a force that is going downward. But in fact, the electron is not a positively charged particle, it's negatively charged. And so the electron will experience a force that is upward towards the top of the paper. Here's another one, and this is one that has to do with induction, okay? So, question. The rail is fixed in, there's a conducting rail and there's a wire on it. If the magnetic field is increasing in strength, which way does the wire move? If the magnetic field is decreasing in strength, which way does the wire move? This is one that we've done previously, but I want you to remind yourself of the details. How do you do this one? And as I say, it's a magnetic induction problem. So look back, remember the details, but take the effort to go through this. The way you practice is by doing it, not watching me do problems, but by doing it yourself. So go back, remind yourself the details. Let's see what you get. Okay, so let's take a look. If the magnetic field is increasing in strength, there's an applied flux that is into the paper or into the screen, and it's getting bigger. And so there's going to be an induced flux, which opposes that change. The induced flux is outward, and that's the blue dots that I'm drawing here. So the magnetic field that's produced is going outward. Now to make a magnetic field that goes outward, again, I'll use my right-hand rule, wrap my fingers around the wire, so my fingers are curling in the direction of the magnetic field. My thumb gives the direction of the current, and that tells me that the current is going to be going this way. So the current is going this way around the wire. And then I look at the force on that current due to the magnetic field, but it's not the induced field, it's the applied field. So in the wire, the current is going upwards. The magnetic field that's producing a force on it is going into the screen. And so the direction of the force that would be predicted is to the right. The force will be to the left. The force will be to the left. So the wire will move to the left. Here's my assessment. Magnetic field's increasing in strength, and I'm predicting a force to the left that's going to make the area of the loop the smaller. And remember, the flux is the product of the magnetic field times the area. So if the flux is getting bigger because the magnetic field is getting bigger, the loop can also make the area smaller, and that will help keep the flux the same. And so that is the same thing that we see happening. If the wire is moving to the left, the loop's getting smaller, and so everything works. Our assessment is just so. So let's dial that back, and then think about the second case. Suppose the magnetic field is decreasing in strength. Which way would it make the wire move? Well, if it's decreasing in strength, the field that's induced is going to try to replace it. And so it's going to be into the screen. So the field is into the screen, and to produce a field into the screen, I have to have a current which is going the other way around the loop. And then if I look at the force on a field into the screen, look at the force from a field that's going into the screen on a current that's going to the bottom of the screen, the direction of the force is to the right. And that will make the loop get bigger, and again, that makes sense because the flux is equal to the magnetic field times the area. If the magnetic field is getting smaller, one way to offset the change in flux is just to make the area get bigger. So everything works out. That concept, check. Moving on. Here's a couple of quick ones for you, okay? 3 laser beams have wavelengths 400, 600, 800 nanometers. The power of each beam is 1 watt. Rank in order the photon energies, and rank in order the number of photons per second delivered by the laser beams. Take a minute, Think about that one. Come up with an answer for both parts. I'll be back. Well, remember, photon energy, okay, is equal to Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength, or if we want to have it in electron volts, we can turn that equation into the energy in electron volts is equal to 1240 divided by the wavelength. Those are the relationships that we've had. But in any case, if the wavelength is bigger, the photon energy is less. And so the smallest wavelength, 400 nanometers, has the highest photon energy. The longest wavelength has the lowest photon energy. We know that that's true. But then let's think about the number of photons per second delivered by the laser beams. Okay, if you're delivering 1 watt in the form of 400 nanometer photons, it's not going to take in as many photons as if you're delivering it in 800 nanometer photons. Suppose I was going to give you $1, and I can either give you nickels, which are worth 5 cents, or I can give you dimes, which are worth 10 cents. I'm going to have to give you more nickels than I am dimes if I'm going to give you $1 because the nickels are smaller. Same thing, if I'm giving you 1 watt and I'm giving it to you in the form of 800 nanometer photons, I'm going to have to give you more photons than if I'm giving you 400 nanometer photons. I'm going to have to give you more of the ones that have lower energy. So the number of photons delivered per second, 800 nanometers is number 1, 400 nanometers is number 3. Related to this, next question. A solar cell is illuminated with 2 watts of light. Is the maximum possible current greater with 2 watts of red light or 2 watts of blue light? I want you to take a minute. I want you to think about that. I'll be back. Now, the crucial fact is this, okay? In a solar cell, a photon hits it, and then it liberates an electron and causes an electron to go through an external circuit. So I have my solar cell. I got photons coming in and hitting it. And then electrons are liberated. But if I have 2 watts of light, and I have 2 watts of red light or 2 watts of blue light, I'm going to get a lot more photons of red light. And so I'm going to get a lot more electrons with red light. And so I'll have a lot more current with red light. And so the maximum current is bigger with the red light, related to that first principle. Let's do another one. Question about decays. What kind of decay, if any, would you expect for the nuclei with the energy level diagram shown in the figure? Go ahead and think about those. Remind yourself of the details of energy level diagrams and nuclear transitions. Go ahead and think about it. I'll be back. Well, in this first case, A, you can see this proton could fall from a higher energy state to a lower energy state. Now it's just dropped from a higher energy state to a lower, so it gives off a photon. It's going to give off a high energy photon. That's a gamma ray. It's basically like an electronic transition in an atom. If I have case B right here, I've got 4 neutrons in that top level. So if I look at, let's start that over again. That wasn't making sense. I've got 6 nucleons over here, and I got 4 over here. So 6 neutrons, 4 protons. That one looks pretty stable. Like you could move a neutron over and make it into a proton. You could do that, but there's no compelling reason because it doesn't look like it's dropped to a lower energy level. So this one seems stable. Although there is a slight preference for nuclei to have the same number of neutrons and protons for light nuclei. For light nuclei. So stable and maybe a little beta minus neutron to proton, maybe. So it's going to be pretty stable, but it might be a weak beta emitter. The third case, clearly I have a neutron up here. It can drop into the lower energy level. Neutron turns into a proton. When a neutron turns into a proton, that's a beta minus decay. We know that that's true because inside the nucleus, the neutron turns into a proton and it subsequently liberates an electron. So we have a beta minus decay for that third state. Now, after you've finished your review and you've done the concepts. I want you to do some synthesis. And what I want you to do is look at the part summaries for the chapters. And series of chapters have these part summaries. And we're looking at things in part 6 and part 7. And if I look at one of the problems, part 7, I have these questions. And this is a question that asks about X-ray tubes. And it's basically an integrated problem that incorporates some of the stuff from the quantum mechanics chapter and some of the stuff from the nuclear physics chapter in one grand synthesis. So I want you to try your hand at some of these problems. And there are some of the similar kinds of problems on the review assignment, which is posted on Mastering Physics as well. But take a look at this one, read it through, think about how you'll answer it. I'll be back. Okay, so the first piece of the puzzle is this. It's 700 watts of energy is delivered to the tube. 1% of it is converted into X-rays. And so I get 7 watts or 7 joules per second of X-rays. And each X-ray has a wavelength of 0.030 nanometers. So as a consequence, I can take the X-rays, I can figure out the energy of an individual X-ray. I can figure out the energy of the X-ray is because the energy in electron volts is equal to 1240 divided by the wavelength. And so I can figure out the energy of individual X-rays. Once I know the individual energy of the X-rays, I can figure out how many photons are emitted. The second piece of the puzzle is I'm going to be thinking about the dose equivalent in sieverts. Now, the RBE for X-rays, as for gamma rays, is just equal to 1. So we can compute the dose in grays, and that will be the same as the dose equivalent in sieverts. We're going to assume that 80% of the energy is absorbed. So here's a question. 80% of the energy is absorbed. There's 7 joules per second of X-rays. So how much energy is absorbed by the body? 5.6 joules per second. And the technician is exposed to the full power for 1 second. So the energy he absorbs is just 5.6 joules. And then I can turn that into a dose in grays, because remember, the dose in grays is the joules absorbed divided by the kilograms of the tissue that it was absorbed in, so I can calculate the dose in grays. And for this and future problems, I want you to go ahead and complete the calculations, and I will post the solutions to all of these slides online. So go ahead and look at the posted solutions after you've had a chance to do that. Now, after you've had a chance to do a little synthesis and put the pieces together, I want you to practice. I want you to practice on past exam scenarios. Now, this exam is going to be a little bit different than previous exams. But the previous exams are a pretty good guide as to the types of things that you're going to see. So I'm going to go ahead and I'm going to ask you to take a look at past exams. I've posted a practice exam on Canvas, and I want you to use that for practice, not just with the material, but also with the technology of answering and uploading questions. I want you to do that. And then go ahead and take a look at a whole bunch more kind of like problems with synthesize all the information. Spend a lot of time practicing. Look over the things that you've done. Try them again. Look over problems that are solved in the textbook that have video solutions, etc., etc. Practice, practice, practice. And you can use this video to do a bit more. And I'm going to show you a bunch of problems. I'm going to start working them through, and then I'll post solutions on Canvas. Okay, first one, and this is from a past exam. Let the sun shine in. So this is about solar cells, and there's a couple of multiple choice questions about it. I want you to take a minute to read this through and then try to answer these 2 questions. So go ahead and take a minute, read it through, do the first couple questions. I'll be back. Now, let's take a look at how you'll solve these problems. I'm not going to solve them. I'll just think about how you would solve it. So the band gap is 1.5 electron volts. And you have to have, and the photon energy has to be greater than the band gap. So the smallest possible energy photon that can liberate an electron is 1.5 electron volts. Then you have to figure out what part of the spectrum that is in. So first, you're going to take that and convert that into wavelength, and then you're going to think about what part of the spectrum it's in. Go ahead and do that, and then before you check the solution. Next piece, monochromatic light is shining in the cell. There's a modest current to increase the power. Now you can't increase the voltage of the solar cell. The output voltage is approximately the same. So the only way I can increase the power is by increasing the current. And the only way I can increase the current is to get more electrons liberated. And we have one photon liberates one electron. So here's the question. I need to have more photons. How do I get more photons? Which one of these, changing it, specifically increasing it, if I increase these, in which case would I increase the number of photons and thereby increase the number of electrons? Think about that and come up with an answer before you check the posted solutions. Next piece of the puzzle is a short answer question. The short answer question is this. The circular cell is exposed to 250 watts per square meter of 500 nanometers light. What is the maximum current the cell can provide? And I want you to show all the steps in your calculation. And first off, before you do this, write them down, because the important point when we're grading a test is to see, do you know what you're doing? Not that you just start sticking equations on your paper and sticking numbers in them, but what would you do? So take a minute to think about the sequence of steps that you would go through. And then I'll talk about this a bit more. I'll be back. Okay, now let's think about this. We get 250 watts per square meter of light that comes in. And the power that the cell absorbs is just equal to the intensity of the light times the area. So I can figure out the power, i.e. I can figure out the joules per second that's coming into the cell. That's the first part. It's 500 nanometer light, so I can work out the energy of individual photons. And I can put that in joules. And then I can take the amount of energy that comes in per second. So I can take the energy coming in per second, and I can divide it by the energy per photon. And if I do that, I get the number of electrons that are liberated, because one photon liberates one electron. And then what current does that corresponds to? Well, that's the number of electrons. But current, remember, is equal to charge divided by time. Oh, and the charge that flows is just equal to the number of electrons times the charge on the electron. And the time is just 1 second. So with that, that's plenty of hints. Go back, complete your calculation, work it all the way through, and then when you've done that, check the posted solution. Next up, I want to look at one about cyclotrons, okay? So here's the question. Beta minus emitters occur in nature, but the beta plus emitters that are used in medical procedures are created artificially. These days are made using cyclotrons. We talked about this, okay? So this cyclotron that can produce a beam of deuterons, which is a nucleus of deuterium, which is an isotope of hydrogen consisting of a neutron and a proton, or a beam of protons. So that's the basic situation. So think about this, how this thing is working, and then we have some questions based on it. And here's the first one. In the picture, a beam of protons is orbiting as shown. What is the magnetic field that produces the circular orbits? And then, suppose you'd made a beam of protons orbiting that leave at a certain speed. To produce a beam of deuterons that exits at the same speed, how would you have to change things? This is a problem about charged particles moving in magnetic fields. Give it some thought, review those details if you need, I'll be back. So if the protons are orbiting like so, okay, protons are orbiting like so, this proton right here is moving in this direction. The force is towards the center of the circle. So I want you to think about this. Given the velocity, given the force, what direction magnetic field would be necessary to produce that? That's a right-hand rule question. So figure that out. Next piece of the puzzle, I want you to think about this. If I want the protons and the deuterons basically to go in the same orbit, okay, remember our relationship for the radius of a circle for charged particles going in them. And if you don't remember that, you can remember that we said that the force necessary to make an object go in a circle, mv squared over r, is equal to the force provided by the magnetic field, which is q times v times b. Comparing deuterons to protons, the question is, let's see, I'm going to have the same velocity, so this is going to be the same. They have the same charge. I want them to have the same speed, so this is the same. It's the same orbits. They want to have the same radius. If the magnetic field is or the mass increases because they're heavier, I'm going to need a larger magnetic field. And in fact, that's what you would do in this particular case. And there's a short answer problem that goes with this as well, and it asks you to consider the reactions that the cyclotron produces. So you produce some isotopes, and these isotopes subsequently decay by beta plus emission, positron emission. And so what are the daughter nuclei of those decay? I want you to work those through. But I'm going to do one as an example, and then I want you to try the other two as practice. So let's look at the bottom one, because there's three separate cases. Okay, but let's just look at the bottom one. Proton plus nitrogen-14 is carbon-11 plus something, and what does it subsequently decay into? So let's think about the decay. Okay, so it's a proton, but a proton's a nucleus of hydrogen. So it's got one proton, one nucleon, plus nitrogen-14, nitrogen's atomic number 7, 14 nucleons, turns into carbon-11, carbon's atomic number 6, plus what? Now coming in, I had 1 plus 7, 8 protons. I've got 6, so what's left over is 2 protons. But then let's look at the number of nucleons. 1 nucleon plus 14, 15 on that side, 11 on this side. So clearly what's left over is 4. And so I get 4 plus 2. I get a helium nucleus. That's an alpha particle. Not a huge surprise because we know that's a very stable chunk of nuclear matter. And so that what I would put for the question mark here is a helium-4. And then let's think about the beta decay. Okay, carbon-11 is going to beta plus decay. And when it beta plus decays, okay, it turns into a positron, which has got 1 positive charge, 0 nucleons. And so what's left over is 11 nucleons, but an atomic number of 5. An atomic number of 5 tells me I'm dealing with boron. And so I get boron 11. So that's how you solve those problems. Take this opportunity to do the other two, and then check yourself with the posted solutions. Next up, I want to think about some magnetic fieldy kind of stuff. So I want you to take this one, and I want you to read it through, and then think about the multiple choice questions. Take a moment, read them through, think about how you would answer them. I'll be back. Okay, so the first question is this. The Earth's magnetic field is produced by circles of electric current deep in the Earth's core. If you're at the Earth's north pole, i.e. the Santa pole, looking down towards the Earth's center, what is the direction of the electric current? Well, the magnetic field of the Earth goes from the penguin pole up to the Santa pole, like so. We know that's true. The magnetic field lines go into the Earth like that. So if I think about the current producing the field, the magnetic field produced by this current points like so. And if I take my fingers and I wrap them so that the current, my fingers are going in the direction of the field, my thumb gives the direction of the current, what do you get? I want you to try that yourself before you check the solutions. Now, protons and electrons in the solar wind travel in large circles around the field lines. The magnetic field is going downward at the North Pole. So think about the direction of motion of the orbits. How would protons travel? How would electrons travel? And in this case, imagine having a top view. Here's a top view. Here's an orbit of a proton. The magnetic field is going downward because I'm imagining myself above the Santa pole and I'm looking downward. The velocity is like so or like so. It's one way or the other. Which way is it? We know the force is directed towards the center of the circle. The magnetic field is directed straight down. Use the right-hand rule to determine which direction the velocity has to be, and then ask yourself, is that clockwise or counterclockwise? Having on the protons double back into the electrons. Try both of those calculations before you check the posted solutions. Now I want to think about this one. So a bike speedometer works like this, and if you have one, you've seen this before. There's a magnet that you put on your spokes, and the magnet goes whizzing by a little coil which is mounted on the frame of your bicycle. And when it goes by, there's a little voltage spike that's produced. And the question is, what will the graph of voltage versus time look like if you're running slow or you're riding fast? Read the question through. Reason this through, think about it, and then I will discuss a little bit of detail in just a minute. Well, initially, when the magnet's far away, there's like no field at all. And then the magnet swings into view, and there's a north pole of the magnet here, so it's making a magnetic field go to the left through the coil, okay? And if the magnet's, and then it says a clockwise current is recorded as a positive voltage. So think about this. If you had an induced flux to the left, the coil is going to make its own flux, which goes to the right. It's going to make its own field that goes like this. Okay, to produce a magnetic field that goes like that, what direction would you need? What direction current would you need? Is that going to be a positive spike, or is that going to be a negative spike? Am I going to get this, or am I going to get this? I want you to think about that. But then too, the flux is going to go one way because you're building up the flux, and then it's going to go away. And so we'll get one spike that's either like this or it's like this. And then I'm going to get a second spike, but in the second spike, it's going to be the opposite. So I'm either going to get that or else I'm going to get this. I'm going to get one of those two. And then sometime later, I'm going to get a second spike when the magnet comes back around again. So think about what that looks like. And then I want you to think about how would it change if instead of going slow, I was going fast? What properties would change? One is the rate of change of flux, but also two, the little peaks that you get will be closer together. So give that some thought, work the details through, and then check the posted solutions. This one has to do with energy levels in rhodopsin, different forms of rhodopsin which are in your eyes, okay? And so 1, 2, and 3 are three different forms of rhodopsin, and which one, 1, 2, or 3 corresponds to red, which corresponds to green, which corresponds to blue. Go ahead and puzzle this one through. I'll be back. Well, this is a question of energy level. So think about this. Photon comes in, and it pops an electron from a lower energy state into an upper energy state. Think about the energy of photons, and think about which energy photon is going to correspond to which color. And you should be able to match up the different types of cones to the different colors. So puzzle that one through before you check the posted solution. Next up, I want to talk about emission of light by in light bulbs with filaments. So halogen bulbs have filaments like incandescent bulbs, but the filaments are hotter, the bulbs are smaller. And if you increase the temperature of the filament over a typical incandescent bulb, what does that do to the energy radiated? What does that do to the peak wavelength? These are two questions about emission of radiation by warm objects. That's a chapter 25 thing. So check back on those details. Think about this question and go ahead and work that through before you check the posted solutions. Next up, if I had the lamp focused into a circle 40 centimeters across, I move the lamp closer, now the light's in a circle 20 centimeters across, how much does that increase the intensity by? That's another thing in chapter 25. Remember the definition of intensity. It's generally power divided by area. If I make the circle smaller, how much does that increase the intensity? Puzzle that one through before you check the posted solutions. After you've had a chance to work through all these problems and a bunch more, you are ready for exam number 2. And that is exactly what we're going to be doing on Friday, April 17th. Full details of how it's going to work are posted on Canvas. Do not hesitate to reach out to me if you have any questions or concerns. But I have every faith that you folks are going to do fantastic. We've got a week to get ready. So I'm looking forward to seeing what you folks can do. I'll talk to you later.